Okay, so the last part of the class that I didn't have a chance to get to, but still has to do with approximations. Remember, we discussed marginals as the how much it would cost, or how much we would make, how much profit we might make from producing one more item if we've produced a certain number of items. We talked about differentials, which allow us to approximate functions at different points that may be very difficult to calculate. And the last part of approximation is linearization. And this is no different than what we've done before. The linearization, or the linear approximation of a function, is the equation of the tangent line at some point, x equals a, right? So it's the equation of the tangent line. We've done this already. We looked at the tangent lines using the point slope equation, y minus y1 equals m times x minus x1. We're going to rewrite this slightly and call it the linear approximation, but it's exactly the same thing. All that we're doing is coming up with the equation of the tangent line at some point a. And we're going to then use it to make approximations, because the tangent line is the best approximation to the function around this point a. So the point that we're looking at is a, and its y value is f of a, because the point lies on the function. So my y1, if we go back to the point slope equation, we can rewrite that as y minus the y value of the point is f of a. The slope m is the derivative, because the derivative is the slope of the tangent line at that point. And then we have x minus a, which is the x value. I'm going to add f of a to both sides of this equation. And what we'll end up with is just a rewritten, linearization, or equation of the tangent line. So f of a plus f prime of a times x minus a. This is what we call the linear approximation to the function. So I'm going to label that L of x, just to remind us that's a linear approximation, but it's the same as the equation of the tangent line. Now, I do want to point something out. When we were talking about the PSA announcements in a pet store, and after we'd made 12, the cost of making 12 was C of 12. And then to figure out how much it would cost to make the 13th, we added C prime of 12 to C of 12. That's what we did to figure out an approximation of how much it would cost to make the 13th item. Now, the reason we did that is because the difference between our 12th and the 13th item, this x minus a, was 1. That was just 1. So we've already used this. We just didn't quite name it what we're calling it currently. So let's think about, you may not remember that example, and that's okay. So we'll do some additional examples and think about how we might use this to approximate functions. All right, let me add a new. From our tangent line, if I look farther away from 8, then there's going to be a much larger difference between the function and the tangent line. So using the tangent line to approximate the function is not helpful. But if we're really close to 8, then the tangent line and the function are very, very close to each other. So let's look at an example where we want to find the linearization of the cube root of x at a equals 8. And then we will use it to approximate the cube root of 9. All right, so here, again, let me just remind you of the equation of the tangent line in this form. That will be the linearization. Right now, the center of our linearization, a equals 8, is called the center, that is 8. So we need to find f of 8. We also need to find the derivative at 8, and then we will have x minus 8. That will be our linearization. So f of 8 is just the cube root of 8, which is 2. To take the derivative, I'm going to rewrite the function as x to the 1/3. And the derivative, we'll just use the power rule here. That will be 1/3 x to the negative 2/3, or 1 over 3 times the cube root of x squared. And we need to evaluate the derivative when x is 8. So I'm going to put 8 inside of the derivative. So that gives us the cube root of 8 squared. The cube root of 8, I can do that first. That's 2. 2 squared is 4, and 4 times 3 is 12. So that's 1/12. Okay, we're ready to write the linearization. The linearization will be f of 8 was 2. The derivative is 1/12. And we have x minus 8. This is telling us that for any x value that I want to use, as long as it's close to 8, this will be a decent approximation for that function value. But it must be close to 8, because the farther away we get from 8. All right, so let's use it to approximate the cube root of 9. And we did this slightly differently in class because we used differentials to do the approximation, but it's the same thing. This is just a little bit more formalized. So right now, to approximate the cube root of 9, I'm going to put in 9 in place of x, and that's going to give me 2 plus 1/12 times 9 minus 8, which is 1. Now, I do want to make a correlation with what we were doing in class. This 9 minus 8, that's dx. That's the difference between our x values. So, and this whole piece right here is the change in y, that's dy. And all we're doing is adding that little dy to our original function value. That's how we get to the next point on the tangent line. So if we continue this, we have a 2 plus 1/12, because 9 minus 8 is 1. And that on the calculator is about 2.0833. If I just put in to the calculator the cube root of 9, it's also an approximation, but we get 2.08008. So they're quite close to each other. It depends on how much error we're willing to tolerate. I'm going to leave the second example to another video, just so that they don't get too long.